Mr. Miller, I'm Coach Physics here. Today we are going to start looking at some two-dimensional motion. So at this point we focused on one-dimensional motion. We did one-dimensional motion, constant acceleration. We stuck with the x direction, but we could have done any direction in one dimension. And then we did gravitational free fall, constraining ourselves to the y direction under a known constant acceleration. Right now we just want to be able to discuss, first off, two-dimensional motion, and then we can put some contingencies on that motion itself. So, we'll start off with motion in two dimensions. So just like we had with one dimension, displacement, velocity, and acceleration, we have the same thing going on with two dimensions, but with just a little bit more to keep track of. So, displacement. Have ourselves a displacement vector, should be like a C there, and we could call that delta r hat. Well, that delta r hat has a magnitude and a direction, and it also has an x and y component. So there's a couple different ways that we could write this out. We could write it out as delta r hat being equal to the magnitude of delta r hat at some theta sub delta r, magnitude and direction, or I should say and, delta r hat is going to be equal to some delta x I hat plus some delta y j hat. X component, y component. So, instead of one dimension, we got two down. Big deal. So, let's just spell the rest of this out, then we can look at the particulars regarding these individual vector quantities. So we've also got velocity vector. Velocity vector, v hat, can be written again as the magnitude of v hat at some theta sub v. Magnitude is how fast it's moving at some given moment in time, and theta sub v is the direction that it's moving in at that moment in time. And then we can also write it as, well, v hat is equal to some v sub x I hat plus some v sub y j hat. So notice now I'm explicitly using I hat and j hat, I hat and j hat. Even though we have subscripts here telling us that, yeah, that's a delta x, that's a delta y, it gets important to be able to treat them separately, because when you start just using numbers for these, you don't have it delta x, you have it 7 meters. 7 meters in what direction? You need the I hat there, because we also could have j hat. So this is where it becomes important to really utilize these unit vector notations and have them written in. One dimension, you can get away with it. Two dimensions, not really. So we've also got ourselves acceleration vector. Got ourselves some a hat is equal to the magnitude of a at some theta sub a, and a hat is also equal to some a sub x I hat plus some a sub y j hat. So this kind of just spells this out, and in terms of these quantities going back and forth between magnitude and direction and unit vector notation, we just go back to what we were doing in the very beginning with vectors. So noting going, I will say to and from, to and from, magnitude and direction, unit vector notation, just in general, we've got ourselves, look for displacement, we've got ourselves that the magnitude of delta r hat is equal to the square root of delta x quantity squared plus delta y quantity squared. So we've got that, and we've also got theta sub delta r is going to be gotten by looking at the arctangent of the y component divided by the x component. That's good. And what else? Well, we've got to be able to go the other way. We've got ourselves that delta x, the x component, is going to be equal to the magnitude of delta r times the cosine of theta delta r. And delta y is going to be equal to the magnitude of delta r hat times the sine of theta sub delta r. So these are just the transformations to and from unit vector notation and magnitude and direction that we've used. And we do it with them all. We'll just write them down just so we have them. Velocity. We've got ourselves that the magnitude of the velocity messy, which again is the speed, is equal to the square root of the x component of velocity squared plus the y component of the velocity squared. And we've got ourselves that theta sub v is going to be gotten by looking at the arctangent of v sub y over v sub x. Again, these thetas are with respect to the positive x direction. You still got to be a little bit careful about adding 180 degrees onto it or not. Knowing if you're in the second or third quadrant, that's the direction that it's moving. You're going to have to add 180 degrees onto it. But this is the direction of motion. Magnitude of speed. Angle is the direction of motion. And then, of course, we've got ourselves the components. V sub x is the magnitude of v times the cosine of theta sub v. And v sub y is the magnitude of v times the sine of theta sub v. All right, so got it for displacement, got it for the velocity. What's left? Acceleration. Let's just go ahead and put that down here too. Acceleration. We've got ourselves the magnitude of the acceleration is again square root of a sub x squared plus a sub y squared. The direction of the acceleration is gotten by looking at the arctangent of a sub y over a sub x. And the x component of the acceleration is the magnitude of the acceleration, not a sub x, multiplied by the cosine of a theta sub a. And a sub y is the magnitude of a times the sine of theta sub a. So hopefully you see there's a very common theme between these transformations. It's all based upon the same vector algebra that we did in the very beginning, and that's pretty much that. So we could have a scenario where the acceleration is 0, total acceleration none, no x component, no y component. What would that really mean? Well, if there's no acceleration, there is no change in the velocity, because that's what acceleration ultimately correlates with, a change in velocity over time. 0 acceleration, no change in velocity, you have constant velocity. That is to say that the object would move at one speed in one direction for all time. Now maybe that direction breaks into an x and y component, that's fine, but it would be uniform motion, or constant motion. Displacement would go linearly with respect to time. It'd basically be like a displacement equals the velocity times the time. And everything would just be in a nice straight line, straight path. But we could also have that the acceleration is non-zero, that it is a constant acceleration maybe. So maybe we have like a rocket that's blasted off and it accelerates at some angle with respect to the horizontal. It has both a component in the x direction regarding its acceleration and in the y direction regarding its acceleration. And those accelerations, we'll say constant for now, produce a linear change in the object's velocity with respect to time in both the x and y directions, which produces an overall change in the object's speed and could produce a change in the object's direction of motion. That kind of depends on if the object has an initial velocity or not, but don't worry about that right now. And then again, with constant acceleration, we'd have that the x component of displacement and the y component of displacement would go as time squared. So we can start putting all those criterias in, and ultimately see what we get out of this regarding these sort of generalized relations for two-dimensional motion. So let us do that. We can even go farther and say that the acceleration is not constant. We have some time-varying acceleration. Then we'd have to start using some derivatives and stuff to quantify things or to write definitions. We'll look at that a little later for those of you that it matters for. All right, so let me bring this. Let me bring this in. Throw that in. I'm gonna have to erase. So have this written down for some reference. But let us do this. Let us say that we do indeed have constant acceleration. If the object is subject to a constant acceleration, messy there, slipping out of my hand. In 2D, 2 dimensions, we have this. Well, we have the x direction and the y direction, which are separate directions. They are perpendicular to one another, excuse me. And well, the x direction has nothing to do with the y direction, and vice versa. They are separate entities in a sense. So we'd have for the x direction, we'd have delta x is equal to 1/2 a sub x t squared plus v x sub I times t. There would be our delta x. We would have ourselves v sub x is equal to a sub x t plus v sub x initial. And we could put a final here, vx final, but it's kind of understood that this is varying with time. So let's just put vx final, sure. So these are the two fundamental time-dependent expressions for constant acceleration in the x direction. Well, we'd also have it for the y direction, right? For the y direction, up until this point, we've only considered just gravity acting, free fall. But it doesn't have to be just gravity. Again, we could have some rocket that's being propelled upward. That's not free fall. There's some other force acting on the object. There's some other acceleration being produced. So what do we have? Well, y direction, we'd have the same sort of form of these expressions. We'd have delta y is equal to 1/2 a sub y t squared plus v yi times t, and vy final is equal to ayt plus vy initial. So those would be the two fundamental time-dependent expressions for the y direction. So what does that do with everything? Well, now we'd have this. Now we have displacement. Delta r hat is going to be equal to, well, it's a delta x I hat plus a delta y j hat, right? Delta x I hat plus delta y j hat, which then expands out. Leave myself enough room for this. Delta r hat would then be equal to 1/2 ax t squared plus v xi times t I hat, so that quantity in the I hat direction, plus 1/2 ay t squared plus v yi times t j hat. That looks a little bit different than just delta x hat, delta x I hat plus delta y j hat, right? Because we have specific forms now of the expressions for delta x and delta y under the contingency of a constant acceleration. This is what we get out of it. If we want to know what the total magnitude and direction are, well, the magnitude of the displacement is the square root of the sum of the squares of the x and y components. So that expands out to be something that looks pretty big. But remember, when this is quantified at some specific moment in time, it's just a number. This is just kind of in general here. We'd have 1/2 ax t squared plus v xi times t, quantity squared, plus 1/2 ay t squared plus v yi times t, quantity squared. And if we wanted to know about the direction, the overall direction of the displacement, we'd have ourselves, that is the arctangent of the y component divided by the x component. So we'd have quantity of 1/2 ay t squared plus v yi times t divided by the quantity of 1/2 ax t squared plus v xi times t. There we go. So what do we do? Well, a, x, and ay, those are constants, because we already said constant acceleration. If we know what those constant components are, and we know what the initial velocity of the object is in the x and the y direction, we can figure out what the total displacement is at any given moment in time in unit vector notation, or we can figure out what it is as a magnitude and a direction. That's pretty much that. And that's great to be able to do. So likewise, we've also got ourselves the same thing going on with a velocity. So mark this off. So now we have for velocity, we have ourselves that, let's do it kind of like here. We've got some v hat is going to be equal to some v x I hat plus some v y j hat. Great, well, what does that equal? V sub x is this, v sub y is this. So I'm leaving the finals off of here just because that kind of makes it seem like it's being at a specific time. Really doesn't matter, but just note that. So we've got ourselves, this expands out into axt plus v x initial I hat plus ayt plus v y initial j hat. There's the total velocity vector written in unit vector notation. And what else do we have? Well, we have commonly, we want to know how fast is the object really moving? What's its speed? Well, its speed under constant acceleration would be the square root of the x component, axt plus vxi, quantity squared, plus y component squared, ayt plus vyi, quantity squared. And we've also got the direction that it's moving in at some given moment in time. We got by looking at the arctangent of a sub y t plus v y initial divided by the quantity of a sub x t plus v x initial. So again, give me a time. If I know or you know what the constant acceleration is, its x component and its y component, and the initial velocities in the x and y directions, all of this you can figure out. How fast it's going, what direction it's moving in. One last thing, right? Acceleration. Acceleration, we have a hat is equal to constant. That was our whole contingency here, right? Well, if a hat's equal to a constant, we have that a hat is equal to some ax I hat plus some ay j hat, and we can get that as x and y components based upon the magnitude and the direction of the acceleration. A sub x is equal to the magnitude of a times the cosine of a theta sub a, and a sub y is equal to the magnitude of a times the sine of theta sub a. If we had the x and the y components, then we can figure out the magnitude and direction. Typically in two-dimensional constant acceleration types of problems, you are given things like, hey, here's the acceleration vector as a magnitude and direction, and here's the initial velocity of the object as a magnitude and direction. Figure out what is the speed at a specific moment in time, what's the displacement at a specific moment in time, what direction is it moving in, and such things. So in order to be able to do that, we have to be able to resolve the constants of the system into their x and y components. Because notice, everything's split up. X component, y component, x component, y component, x component, y component. That's how we're going to work in 2 dimensions. Or if we switch to 3 dimensions, that's how we work. Keep things separate. We can always put them back together to find an overall magnitude and direction. But working with them separately is the way to go about it. Mathematically, it's the easiest way to approach it. So given a hat is equal to some magnitude of a at theta sub a, and v initial hat is equal to some magnitude of v at some theta sub v, we can determine all aspects of an object's motion. Again, by breaking things into their x and y components. Say resolving. So again, I'm going to write the same thing down right there. We have that a sub x is equal to the magnitude of a times the cosine of theta sub a. A sub y is equal to the magnitude of a times the sine of theta sub a. So that's how we resolve the initial velocity, the initial acceleration given a magnitude and a direction. And then for the initial velocity, we would have ourselves that Vx initial is equal to the magnitude of V initial times the cosine of a theta sub V initial. I should put a little initial. And Vy initial, the initial velocity in the y direction, is the overall initial speed of the object multiplied by the sine of its initial motion, or initial direction of motion. So when we start time, that is, an object can already be moving in a specific direction with a specific speed. This allows us to go ahead and resolve that, that initial velocity into its x and y components. The acceleration is constant, so those stay throughout time for a constant acceleration case. Again, once we have these 4 quantities, the only thing we need to note is, hey, what time do you want to know something about it? Evaluate, evaluate, evaluate. But this is what we've got to be able to do. All right, so lastly, we could take this into another realm in which the acceleration is not constant. And things don't look so bad, actually, but it's all contingent upon the behavior of the acceleration, how it really ends up becoming. Erase this stuff, and leave that. We'll say if the object is subject to an acceleration that is not constant, what do we have then? What do we got to work with? We still work in terms of x and y components, But we need to know how the acceleration behaves as a function of time, ultimately. Because we've got ourselves that x hat, the position, is going to be, sorry, I'm getting this messed up here. We've got ourselves that a sub x is defined as dv sub x dt, and a sub y hat is defined as dv sub y by dt. So in order to figure out what the acceleration is in terms of its x and y components, we'd really need to actually have a function of it or know how the velocity varies with respect to time. Or we've also got ourselves that v sub x itself is defined by dx hat dt, and v sub y is defined as dy dt. So this is what we'd ultimately break things down into. We need to have some function that describes, well, either the velocity with respect to time, the acceleration with respect to time, or most typically the position of the object with respect to time. So if we know that, then we can figure out the time variance of the velocity and time variance of the acceleration. And that would kind of be that. So how would we write out these vectors in terms of their total compositions? All that we could do is rely on this. For constant acceleration, we have very formal expressions, but that was for a particular model behavior. We change the model behavior, we change how we get to quantify these derivatives here, or obtain expressions from them. So the best that we can ultimately do is say that, well, a hat is equal to some dv sub x hat dt, we can put this I hat, change that to I hat, plus dv sub y by dt j hat. Its magnitude would then be equal to the square root of dv sub x over dt quantity squared. This isn't the second derivative, this is the square of the first time derivative velocity, plus dv sub y by dt squared. And we have ourselves that theta sub a would again be gotten by looking at the arctangent of dv sub y over dt divided by dv sub x over dt. And then we do the same thing for the acceleration, for the velocity. We'd have ourselves that v would be equal to some dx by dt I hat, that's v hat, plus dy by dt j hat, and have a magnitude equal to the square root of dx by dt quantity squared plus dy by dt quantity squared. There's its speed at some moment in time when we evaluate it. This just gives us the function. And theta sub v, gotten by the arctangent, that's a big one. Arctangent of the quantity of dy by dt divided by dx by dt. And again, we'd have some function that describes the variance that we could break into its x and y components. So it comes in to say that it depends. This is generalized. That's what we do. Not something we're going to look at a whole bunch, but it is worth stating out. You may see a problem or so in homework that deals with acceleration that is not constant. And this is how it has to be approached. All right, so best to you. Till next.